Okay, this is where also I'm going to deviate from this, and that is, Lavoisier, what he did was he took observation, and then what? You know, okay, after observations, was this met with skepticism, predicting, testing, revising, in this order? Not really in this order, so it's a little bit confusing there. So when we take observations, the first step is this. What do we do with those observations? So you can take observations of a dog, and so it's like, let's say you're trying to observe Dobermans, right? And so you're trying to understand Dobermans, and does that mean you have to observe every single Doberman out there? Or can you observe a bunch of them and then make some kind of generalizations about those, right? And so typically what we do is we'll take observations. Now, do we take observations of every single one? No, but we'll take as many observations as possible. So let me show you some observations here. Here. These would be some quantitative observations. Some observations, that's the numbers for, etc. These would be observations of some chemical properties, like how things behave, how these chemicals behave. And so we take these observations here, and then what do we do? Do you meet those with skepticism? Well, obviously we'll want to take accurate observations, so we might be worried about how those observations were collected and this kind of stuff. We got a bunch of observations. Now, what's the next step? You know, so Lavoisier, you know, he took some experiments, he did some experiments, and then what's the next step from there? Well, the next step from there is this. And this is what's missing on the slide. Typically, the next step is to look for patterns or trends. And so let's start off with another example. Maybe, you know, these are a lot of observations here, but and when you look at that, you know, what can you conclude from that? Well, it's very difficult to conclude anything. But let's try another example here. That other example would be of this. You know, one of the observations I remember as a child is the apple falling from the tree. Have you heard that? The apple falls from the tree and hits who is that? Newton on the head. You've heard of that one? You've probably seen it. And so apple falls from the tree, hits Newton on the head. Right? This is the observation. And so, well, do you want just one observation? Probably not. It's like, okay, you look at one Doberman and then you know all of them. Would you say that's correct? No. So you try to take many observations. And so rather than, let's say this would be the apple, maybe you take this and then you want to be more quantitative. And so we'll do an experiment. Experimental, that means we might grab a stopwatch and then time it. You know, I remember doing this in physics with metal balls. Took metal balls and then timed how long it took to hit. Sometimes our timing was off a little bit, but anyway, we did this. And so we take observations. Okay, so it seems that there's a pattern here. You know, each time I drop it from this height, it takes this amount of time. Right? This consistent pattern. What happens if I increase the height? Well, it's going to take a little longer, right, to impact. And then you do that, and so you look at the apple dropping from the tree or the pen falling on the counter, and then you see patterns develop, trend. And the higher the pen is up, the longer it takes. Simple, that's qualitative. Or we could do it more quantitatively. You know, from this height it takes this many seconds, from this height it takes this many seconds, and we can generate a table like we saw there. Now, when we have these patterns and trends, you know, we want to define those in the simplest, most compact way possible. And the simplest, most compact way possible of defining something like this is to come up with a mathematical equation. You know, a mathematical equation, which we call a law. And so, if you've had some physics, you would be familiar with Newton's laws. Have you heard of Newton's laws? Newton's laws are just these mathematical definitions of the patterns that Newton observed. Right? That's it. And so Newton's law has one for this. You know, how long does it take? Actually, sometimes the math is a bit complicated. How long it takes, based on distance traveled, et cetera, et cetera. So sometimes the math is complicated. So Newton had to actually during Newton's times the math wasn't sophisticated enough. So Newton had to work on developing new mathematics. What was that? To help describe these patterns, called calculus. And so Newton and some other guy, Leibniz, I think, developed calculus to describe these patterns that were observed. And so that's it. And so these laws are often called empirical equations, empirical mathematical equations. We'll just call them empirical equations. And this word empirical, have you heard that before? What empirical means? Empirical means from observations, based on observations. And so, these laws based on observations means that Newton could make predictions. So from this height, it would take this long. From this height, he could use the patterns to figure out how long it would take to hit the table. So that's it. Okay, the same thing, even though you don't see it here, it's the same thing we would do. I mean, chemists and scientists in general do this. They will they'll look at this. I mean, there's a lot of data here. And when you look at all this data, you see any patterns there. And that's what scientists would do. They'd look for patterns. Maybe there is a pattern there. Maybe there isn't a pattern there. It's like, it's like a dog. Let's say you're looking at Dobermans or something. Do you see a pattern there? Maybe there is a pattern. Maybe there isn't. If there isn't a pattern, then you need to study each and every Doberman, because each and every Doberman is very unique. And they're going to have unique properties, right? That's based on their, or are there some patterns? Some similarities, like, well, Dobermans are kind of big dogs rather than small dogs. So that's a pattern, right? Big dog versus small dog. Adult Dobermans are big compared to adult terriers or something like that. And so we look for these patterns. We kind of group it. So when you look at this is looking like, wow, is there any pattern there? So you have to work at this, and this is what I did, and other people around me did. We took lots of observations and we started looking for patterns. Sometimes we'll graph things out, to see maybe there's some mathematical pattern. Sometimes we won't, kind of thing. But anyway, it's better because when we think about studying, some people will say, yeah, you don't need to bother studying about Dobermans. You just, all you need is Google. And then you'll know everything you need to know about Dobermans. Is just Google it. But is that really true or accurate? No. You couldn't do that. We're going to have to know, we're going to have to take our own observations, and then, well, that doesn't mean that we shouldn't research and see what's already been studied about them as well. And so as far as our study of science goes, we're going to do things using a multi-pronged approach, which we'll talk about shortly. So observation, yes, individual observations. And hopefully we can see some patterns, because if we see some patterns, that means we don't have to observe everything. We can kind of make predictions about certain things, certain behaviors, certain properties of things. Okay, if these patterns are very reproducible, that generates a law. Now, what's the difference between a law and a rule? The rules of nature or the laws of nature? What's the difference? A rule or a law? Well, it turns out we use these differently. And it has to do with exceptions. There are a lot of exceptions to the rules, but are there very many exceptions to the laws? In fact, there should be no exceptions to the law. And so the law here, a law of nature, is quite a bit different than like a legal law. You know, in a legal law there could be a lot of exceptions, but in a natural law there shouldn't be. In fact, there's laws of thermodynamics which were developed in the 1800s, and people were looking for exceptions actively, and there's still people actively looking for exceptions to the laws of thermodynamics, because if they can find an exception to the law of thermodynamics, they might become very rich. Because laws of thermodynamics deals with energy. And so some people are trying to develop like perpetual motion machines, you know, where they can generate energy from nothing, basically. And if you could do that, then you have a limitless supply of energy. And so for hundreds of years, people have been trying to do this, generate or develop a perpetual motion machine, but nobody's ever violated the laws of thermodynamics, even though they continue to try. Okay, there are some laws that we use. Some laws that we use, like the gas law, there are some known exceptions to that, but people already know that. And they know why there's exceptions to that, because they want to make the math simple. Make the math simple, they're going to generate some exceptions, versus having to use calculus for things or having to do this for other things. You know, they just try to make it simpler. But in general, we don't see exceptions. Whereas rules, we'd see a lot more exceptions. So that's the difference. But, you know, a lot of people, where do these laws come from? These laws come from factual observations. Factual observations are memorizations, you know, or, you know, written observations, this type of stuff. That's where that comes from. But there's been a big push away from memorizing things or looking, and that's not the way we do science. The way we do science is we're going to have to memorize a lot of things. We memorize a lot of things so that we can see these patterns. You know, these patterns that develop. And so there's an element. But do we want to memorize everything? Like, for example, if you want to know about Dobermans, do you want to memorize every single Doberman that exists in the U.S.? You know, factual knowledge about so-and-so's Doberman versus so-and-so's? No, this is too much. And so the same thing with us. You know, we don't want to memorize everything here. You want to memorize everything here in order to understand it? No. What we want to see is, can we see patterns? Those patterns will help us. You know, it looks like these are all random, whatever else, but they are organized by this number here. Talk about that later. But this isn't it. You know, the scientific method goes beyond this. And so the next step here is this. With Newton's laws, you know, Newton's laws got people to the moon. But we need to know a little bit more about this. And so the next step in the scientific method is the hypothesis. Split up the word, hypothesis. And so we have this law, and the question comes about is why? You know, I don't want the pen to fall down. I want the pen to fall up. And so I'm going to watch this pen, and I'll watch it, and I'll watch it, and I'm going to wait for it to fall up rather than fall down. If this thing falls up, then you know what? That violated Newton's laws. And then we'll have to rethink physics. And so, okay, well, then people might be thinking, you know, is it really worth spending your time waiting for this to fall up rather than fall down? Because then people are going to start thinking, okay, what's causing this to fall down? Why doesn't it fall up or fall to the side, to the left or to the right or wherever, or go in some kind of squiggly motion down, you know, rather than straight down? And so people are starting to think, well, there must be something pulling it down rather than pulling it up. What is this thing that's pulling it down rather than up? I know what the law is, and using the law, I can predict the time, you know, the stopwatch time. But there's something missing there, you know, and that is, why is it being pulled down rather than, why doesn't it be pulled up or pulled to the side or pulled to that side? You know? And it would be gravity. Right, and so the hypothesis was that there's this invisible force called gravity, which is pulling it down. And so what a hypothesis is a hypothesis, and this is called a tentative fundamental explanation or description of the law or the phenomena that we're, I'll just say tentative fundamental description. It's just describing what's happening at a more fundamental level. And what the more fundamental level is, there's something pulling it down, actually down to the center of the Earth. I mean, if you dig a hole, it'll just keep going down, until and so a lot of things were just stopped at the law stage, but pretty soon you start thinking more about this. You start thinking, why doesn't this happen? Why doesn't that happen? And then you try to come up with a more deeper understanding of this. And this would be the deeper understanding of this. But, this is where we come back to this slide here. This is where the skepticism comes in, because somebody's saying, invisible force pulling it down. I don't believe that. What is this invisible force? I got to see it to believe it, right? That's pulling this force of gravity. This is all made up. And so this is also part of the scientific method. Skepticism is a crucial part of the scientific method, because the reason why science works and the reason why these laws hold is because of the skeptics. Science, the way science works is it's self-policed, and the way it's self-policed is by peer review. And so when I started off in science, like say at UCLA and then at UCSB, I had to get used to something. I had to get used to very harsh criticism. I present ideas and then they're very harshly criticized. They're very harshly criticized because what they want to do is they want to make sure that any kind of junk science is filtered out, or any kind of speculative stuff is filtered out. And so if somebody proposes this, somebody else might propose something else. There's an invisible hand that comes up and grabs it and pulls it down. Something like that, or there's some foot coming from the sky kicking it down, something like that. And so there's going to be different hypotheses, but what's going to happen is that there are going to be supporters and people who are against the particular hypotheses, but eventually what happens is the people, the skeptics, are going to be won over. Maybe not 100% of them, but at least the ones who are rationally thinking about this, and then we get to a stage called a theory. And so the only difference between a hypothesis and theory is a theory is accepted or generally accepted and if you can't read my writing, let me know. Accepted fundamental description. And so the hypothesis of gravity was proposed and then tested in different ways. And so, that was skepticism, was testing and revision or whatever else. But a theory must do not only this, which is provide the fundamental description, but it also must do something else. And that is, it also must be able to predict unforeseen observations, or phenomena, or results. Just use those. In other words, for example, this. Okay, so we have this theory. Now, let's say we're on the moon, and I drop the pen from the same height on the moon. Would it take the same amount of time as on Earth, or would it take a different amount of time? Well, we could go to the moon and measure it, right? Or we could use theory to predict it. And so this would be an example of an unforeseen observation result. And that is, we use a theory to calculate how long it would take for the pen to fall and then see. Now, if the time matches the theory, then that's good, because that reinforces the theory. If it doesn't match, then the theory's got to be revised or abandoned. So this is it. Okay, then not only that, but this should also if this is the accepted fundamental description, then we should also be able to derive all the original laws based on the theory. And so once we have the theory of gravity, gravity is this mass A being attracted to mass B, and the mathematical equations which dictate the attraction, the force of the attraction between the two masses. Once we know the mathematics of the theory, we should be able to backtrack and derive all these laws that were originally determined based on empirical observations. But when we derive the equations from theory, we don't call them empirical equations. When we derive equations from theory, we give them another name. If the equations come from theory, we call those theoretical equations, or we can call them like ab initio type equations or calculations, or it could be a mix. Sometimes it's a mix of theoretical and, because sometimes the mathematics of the theoretical are very very difficult. And so we have things that are semi-empirical. Semi-empirical would be part empirical, part theoretical. But if we know theory, then that means we don't need to take individual observations, because we should be able to predict all the observations if we know the theory and the theory is sound. So if I know the theory of the Doberman Pinscher, then I don't have to ever observe any Dobermans. I can just predict how they're going to behave, what their properties are, right? Although a living system like that's too complex, but for chemical systems, it's not as complex. So for example, if I know the theory, I can predict how hydrogen is going to behave, or oxygen is going to behave, or water molecules are going to behave, right? Rather than observing everything. Yeah. But the theory is and can be very complex, and so we take a multi-pronged approach in chemistry. In chemistry, we need to have some factual observations memorized, and we need to have some of these patterns memorized. But it'd be nice not to. It'd be nice to have a command of the theory of chemistry so that we could predict anything. But the math of the theory is way too complicated. And therefore, we are not going to have a full command of the theory. We'll just use as much theory as possible to minimize the amount of memorization we do. But in this class, we're going to do both. We're going to do this two-pronged approach in which we're going to memorize a lot of observations and patterns, but at the same time, we're going to try to understand as much of the theory of chemistry as possible in order to understand the behavior of matter, the properties. Just as you would for dogs, you would probably read books, theory of the psychology of dogs or whatever, and then take your own observations and look for patterns, and then come up with an understanding of the properties of the Doberman. Would a theory does not convert into a law. What a theory does is a theory predicts new laws. So for example, here the theory could predict new laws which we could use to do things, to make predictions. In fact, in chapter 2 we're going to see just that. But all a law is it's just a mathematical equation. And so a law doesn't matter, what the basis of that equation is. A law just takes a pattern and comes up with the math that describes the pattern. Where did that pattern come from, and why does that pattern look the way it is? That's the theory part of it. And so you wouldn't want to convert a theory into a law, because you'd lose that. A law is a much lower level of understanding of the phenomena than the theory. Theoretical understanding is the highest level of understanding. So if you want to understand gravity, the theory, if you want to understand this pen falling, we don't study Newton's laws. We use Newton's laws to do calculations, but we don't really study it because there's not much to study about Newton's laws. Newton's laws, you might have seen it, F equals ma. F equals ma. Okay, you could study that as long as you want, but what are you going to get from that? You know, oh, I know what A is, 9.8 meters per second per second. So, what do you do with that? You know, and so a law doesn't really, you know, okay, now I have this law. Can I use that law to predict new laws and new unforeseen results? No, I can use this to predict lots of things, but they're all things based on this force, this is mass, this is acceleration, all things based on that. Now we need the calculus to get the time out of this. You know? So we could get things based on that. And so if I'm understanding your question correctly, then yeah, we wouldn't want to use a theory and convert it into a law. We would want to predict new laws based on the theory. I can give you an example of a new law that was based on theory. A new law that was based on theory is this. In chemistry, there are competing hypotheses about matter. You know, what is matter made out of? Matter is the physical material of the universe. But if you take that matter, let's say I take a copper penny, and I break it into smaller and smaller and smaller pieces, and smaller and smaller. What is the smallest piece of a copper penny I can have? The smallest piece of a copper penny, and this is why I don't like its original definition, you might think it's a molecule of copper. If I have a copper penny, the smallest unit particle of pure substance, copper, would be a molecule. Well, that's not the case. The smallest piece of a copper penny is what we call a copper atom. It's like a little ball of copper. If we take that copper atom and break it in half, we don't get two smaller balls of copper. You know, in fact, it's no longer copper. We get something called subatomic particles. Those subatomic particles don't behave like copper. We get protons, neutrons, and electrons, and we can't call a proton a copper. A proton doesn't behave like copper at all. It's one of those subatomic particles that are put together. Now, if we go to a bigger piece, we can have two copper atoms, so two balls of copper stuck. Three copper atoms, three balls of copper stuck. And so that was one theory. It's called atomic theory. That is, the smallest piece of matter is called the atom, atomic theory. The other theory was this, hypothesis, since neither was generally accepted at the time. The other theory was that the smallest piece of copper is infinitely small. That is, you can keep cutting it into smaller and smaller pieces infinitely long. You'll just have a very, 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 very tiny piece of copper, right? And you can keep cutting down into smaller pieces of copper, rather than, oh, you stop here because this is the smallest. And so these were two competing hypotheses. Well, the atomic theory predicted this. The atomic theory predicted a new law. Atomic theory predicted the law of multiple proportions. That is, the law of multiple proportions means that these atoms combine in simple whole number ratios. So for example, water is two hydrogen atoms, two balls of hydrogen, and one oxygen atom, one ball of oxygen. Two hydrogen atoms, one oxygen. Whereas the competing theory predicted that it doesn't matter because I could have 2, I could have 2.1, I can have 2.03, I could have 2.56, I could have any amount of hydrogen I want, just cut it wherever I want and add it to oxygen. And so rather than having 2 hydrogens and 1 oxygen, I could have 2.1 hydrogens and 1 oxygen, or any multiple in between. And so this is one of the deal breakers for the other theory. When people started looking at how the atoms combine in what ratios, they always found simple whole number ratios. So for example, water is H2O. Do you know what hydrogen peroxide is? H2O2, which just reminds me of a joke. You probably heard of this joke. Two people walk up to the bartender. One person says, "I'll have an H2O." Oh, okay, here you go. And the person's friend says, "I'll have an H2O2." H2O2. Well, the person's friend ends up dying from drinking H2O2 because H2O2 is toxic, right? Hydrogen peroxide. But anyway, is there an H2O 1.5? H2O 1.9, 1.98, 1.98345? Is there? No, and so this is the case where the theory, atomic theory, led to a new law. That new law wasn't developed. It wasn't observed yet, and nobody had delineated it. And that new law is the law of multiple proportions. That is, when you look at these, what we call molecules, not everything forms molecules. We also have compounds, like quartz, Quartz is SiO2. 2 oxygens, 1 silicon. Basically it was used, so that's number 2, is the predict part. Those predictions can be new laws, or they just can be simple observations. But getting back to it, this here. And so this, I don't like the way this is organized. This is not how, science. When I ask this question to my students, especially the ones who had biology, always start here. You start with a hypothesis, right? And so if I ask, what is the scientific method? Well, start with a hypothesis. I never started with a hypothesis. It's way too difficult. Okay, you start with a hypothesis. Tell me the hypothesis. Here. What's your hypothesis? To me, that's just an incredibly difficult thing because, the science that we did was very simple. You have something like this. Is there a pattern? Is there no pattern? If there's no pattern, we keep looking. And so here's where I'm going to deviate. When I ask you what the scientific method is, I don't want you to write a chart like this. I just want you to write it out like this on the board. Okay, do it the way I did it. Even if the way I did it stinks or is confusing or doesn't make any sense or doesn't agree with the book, do it the way I do it, because then you'll get the maximum number of points. If you don't like the way I do it, then be a skeptic. Confront me on it, and then let's do this properly via peer review. I don't mind being challenged on stuff. In fact, I welcome it. When you're into science, you always welcome people challenging you because you don't want to go up in front of a huge audience and be embarrassed at that time. You want to figure out all the holes in your work before going up and presenting it to whatever conference you're at. You want people in your lab to first make sure, and then beyond that, people in your department, people in the school, then go off to the big national conference or international conference and present it. But if you go to the international conference and there's some big holes in your work, that's not the place you want to find out because it would be pretty embarrassing. And so if you don't like the way I do it, that's fine. That happens all the time in science. All the time. People work it out. Right? Something. But anyway, features of the scientific method. Features of the scientific method: observing and then proposing a hypothesis. So I gave you observations. Do you propose a hypothesis next? To me, this is ridiculous. No. It's ridiculous because you got to first look for patterns and then propose a hypothesis, or look for some law and then propose some hypothesis. But just looking at the observations initially and then proposing a hypothesis is difficult. But I know what they mean here. What they mean is obviously you're going to be looking for patterns. Obviously you're going to be doing all these things in order to propose a hypothesis. But I'm just spelling it out because it's very difficult. Proposing a hypothesis. For example, this. You're watching the apple fall from the tree. It hits you on the head. Oh, I propose gravity. Is that, it doesn't quite work like that. Okay, being skeptical, scientists are skeptical in nature. Predicting an outcome that should result if a hypothesis is true, this is on its way to becoming a theory. Testing the prediction by an experiment. So here I'm going to deviate totally from the book and do it this way. Okay? A lot of people hate when I deviate from the book because they want to use the book as reference. But what you should do is this: I used to, when I was a student, I used to study from the book. I like to study from the book. Because the book is the most thorough and detailed reference that you have for the course material. And so when I transferred to UCLA, the book was my most important source. So what I do is I'd highlight the book, I would annotate the book, with my little notes here and there, and then highlight, right? That's the way I was taught to study. But I quickly found out that didn't work for me anymore, especially when I got to UCLA, because at UCLA, our book is kind of thick. It's 700 pages. At UCLA, I took this engineering class. The book was 1,600 pages. 1,600 page book in 10 weeks. 1,600 pages of literature, probably it's okay. If I took literature class that had 1,000 pages of reading in 10 weeks, I was able to do it. Right? That wasn't the problem. But at the same time I was taking literature, I was also taking engineering. This was an engineering class, 1,600 page. So I timed it. I read 10 pages of literature, timed how long it took. I read 10 pages of the engineering book, timed it. You know how long it took me to read 10 pages of literature? Just minutes, right? I don't know. I forgot the exact number. But when I was reading the engineering, 10 minutes? No. 30 minutes? No. 10 pages took me 2 hours to read. 2 hours? 10 pages in 2 hours? There's no way I was going to read that book. And then my professors are telling me, read the chapter 5 times? Impossible. There's not enough time. Mathematically impossible. So then I thought, well, if I can't study the way I've been studying, which is just based on the book, then I have to change. And so I did change, and I completely changed the way I study. I stopped annotating the book. I stopped highlighting the book. What I did instead was I took notes, in class. I'd write down my notes. And I try to write as complete of notes as possible, but it's difficult because I couldn't write very fast. When I was in high school, I had a professor or teacher in high school. He always said, learn shorthand. That's going to be, if you can do shorthand, you'll get A's in all your classes. I never learned shorthand. I was a slow writer. And so I missed a lot of stuff. But what I tried to do is I tried to schedule my classes like this. I tried to schedule my class so I had a break after class. And so right after class, I remember stuff that I didn't write down. And so I'd sit down there and go through my notes and then write in all, fill in the blanks essentially. The stuff I remembered, but I was too slow to write. And then I get it as complete as possible. Okay, after doing that, there's still confusing aspects of the notes. This didn't make sense, that didn't make sense. And then I do the reading, because I couldn't read 1,600 pages. There's no way. So what I do is I'd see where in the notes I got confused. Where in the notes I got confused, I'd hit the book, this is an engineering book, and then I'd just read that very carefully, that section, so that I understood it. If I couldn't understand it after reading that section, I'd read that section like 1 time, 2 times, 3 times, 4 times, 5 times. I'd read that section. That's not reading the whole book 5 times. It's reading the sections that you're confused with 5 times. That's doable. That's not mathematically impossible. That's totally doable. That's what I did. The stuff that I understood, I just skimmed or I skipped entirely. I understood that, so there's no reason to read it for me. If I still couldn't understand it in our book, I went to the bookstore and I went to the library. I went to the bookstore to look at the next level class. So if I was taking Engineering 101, I'd look at Engineering 102, look at their book. Or I'd go to the library to look at other books at the same level and then read that and see if it made more sense in other books. But basically it boiled down to this. It boiled down to having a set of notes. Now when it came time for the final, I never opened the book. Because the book was too many pages to review. I would just open my notes. So if I had a 1,600 page book, but I had 100 pages of notes, I could go through 100 pages of notes in no time, especially because I went through them repeatedly. Every week I'd go through them It's quick, and I was preparing for the final. So at least once a week, probably more than once a week, I'd read my notes from page 1 to the end. Wouldn't take me very long, and then I'd have it memorized. So that's what I did for studying, and now that way it also did this. I didn't care what the book said. I cared what the professor said, and that really helped me focus in on what the professor was talking about and the way the professors do things. Some professors at UCLA didn't follow the book at all. They were all over the place, but still, when it came to the test, I knew what to predict, because I knew what they were talking, or what they talked about, or what they had to discuss, not what the book said. And so I deviate, from here. I'm just showing you the slides because this is what the book's going to say, but I deviate from that. And so what you should do is concentrate on your notes, not necessarily what the book says, okay, for this. And so if I ask you what the scientific theory is, I don't want observation and then hypothesis. I want observation followed by, that kind of stuff.
But by the book, right?
But by the book, by the book, because there are going to be things that are confusing or things, and then there's homework also. There. You need the book as a reference. It's this chapter in particular. I'm deviating quite a lot. Other chapters I follow right along. It's just the way the scientific method is done. Here, the way I'm presenting the scientific method is how I did it, and all the people around me were doing science. What do scientists do? They do this. They take down observations. They observe nature. They look for patterns in nature. They try to understand nature, how it behaves. That's what we did. Because once you gain a certain understanding, then you can try to make predictions. If you got this theoretical thing down, then you go. And this is what was happening. It used to be, I was always interested in how things work, because I didn't tell you. I started off as a geology major, but I was a geology / automotive major, because I was thinking, I like to work on cars and that kind of stuff. So I was thinking maybe I'll major in automotive. And so I was interested in how things work. But once you understand how things work, then you can build things. And so, for example, in the old days, catalytic converters used to be filled with platinum. And, catalytic converters used to be things that people would try to steal because platinum is expensive. And they could recover the platinum out of the catalytic converter and sell it. And so people were looking for new catalytic converter materials, what we call catalysts, that didn't have platinum in them. And so there are two ways you could do this. You could do this strictly from the observational approach. Observational approach is, I'm going to look for something cheaper than platinum, so let's find something cheaper and then test it. Test it. And so they just take random things off the shelf and test. Does this work better? Does that work better? Does this work better? Maybe they'll get lucky. They'll get lucky and find something that works better. But then that's kind of just taking, in a way, random guesses and seeing if it works, right? Versus if you had a more theoretical understanding. If you had a more theoretical understanding, then you might go, well, platinum, what would be similar to platinum in terms of properties, that's a lot cheaper, and then target your catalyst, your search for catalysts. But we need both approaches because the theory is very tough. Do you guys know about the blue LED? The blue LED? The red LED has been known for decades. Red LEDs have been around. But red LEDs are just red. That's it. And then somebody developed the green LED. Green LED's been around a lot shorter, but they found the green LED. And that set up the search for the holy grail of LEDs. The holy grail of LEDs is the blue LED. Because once people got the green LED and the red LED, then they only need one more color to make all the colors in the rainbow. And what color is that? Blue. Because if you have red, green, blue, you can make white light. White light has all the colors in the rainbow. And so this is happening when I was a student. People were searching. You had your experimental people who were just mixing up different chemicals. They had some kind of idea, mixing and then seeing what happens. And then you had your theoretical people. The theoretical people were thinking, okay, if I tweak this or tweak that, maybe I can get blue rather than green. Do you know who eventually won out? Who eventually won out was a person who tried to use both, some of the theoretical knowledge and the experimental knowledge. The experimental people will make a whole bunch of different formulations. This is like the same thing as in drug design. In drug design, obviously, you don't want to have to do and make thousands and thousands of different drugs to see which one's the most effective. But that's exactly what they do. They have these microreactors with 1,000 little pots in them. And in those 1,000 pots, they make 1,000 different formulations of the drug and then test each of those individually. Wouldn't it be better just to make one? And so then you have the theoretical people just figuring out, okay, which one's the best to make and make that one. Right? Well, which one wins out? Well, it turns out you have to use both because the theory is so difficult. People are thinking, I don't need to memorize anything. Well, that's wrong. You do. We have to take a two-pronged approach. There's got to be some experimental work, which is like memorization, and there's got to be some theoretical work. And the theoretical work is very difficult. So anyway, the theory is what we're ultimately after. So here it says, upgrading the hypothesis to a theory. Yes, a theory. If we knew the theory and we could apply it, then we don't even have to conduct experiments because the theory should be able to predict the outcomes of all the experiments. But we aren't quite there. During this process, all throughout the scientific method, there's communication involved. This communication is called peer review. In peer review, there's a big difference. There are some places where you can publish work without peer review, and you have to be careful, versus places where it's peer reviewed, and you can't just publish anything. And so on the internet, you can pretty much publish anything you want without peer review, without skeptics coming in and saying, what the heck are you thinking? And so this is the communication aspect here. During the scientific method, there's always communication in the peer review process. And that peer review, again, is just to weed out the junk science. There's still a lot of junk science that gets published, but that's not peer reviewed. So there's a big difference between peer review and non-peer review science. And then they talk about the law here. The law is the summary of a pattern of regularity detected in nature. In order to be classified, the law must have no exceptions. Okay, that's all okay, but it seems out of place here for me, because this is at the end of the scientific method. At the end of the scientific method, do we have the law? No, at the end of the scientific method, you should have the theory. And so the law is not the ultimate aim of the scientific method, although I don't know if you read the text, it might not come out this way. But this is from the textbook, so I'm not sure why they did it in that order. All right, but what about chemistry today? Well, Lavoisier, what he's going to do is he's going to run those experiments and then look for those patterns and make predictions. You don't have to know about those experiments at all. But chemists today, what do they study? They study matter. What do they want to know about matter? They want to know how it behaves. How does matter behave? Well, how do you understand how matter behaves? Well, you have to take observations. You watch matter and you try to understand the theory underlying matter. Maybe that's reading books. It's like understanding Dobermans. You watch Dobermans and you read about them. Right? Well, this is the same thing that chemists do. So chemists study matter Okay, what do they want to know about matter? They want to know its properties. What types of properties are there that they want to understand? They want to understand what were the two types of properties I talked about? Physical properties and chemical property. Well, matter and its changes from one substance to another. Its changes from one substance to another. That sounds like transmutation. That sounds like turning lead into gold. Does matter transmutate like that? No. And so what they're talking about here, they must be talking about the chemical property. And so this sentence I have an issue with. Chemists study matter and its property. Well, it's saying more than that. In fact, I'd like to rewrite this whole sentence here. I didn't do that because I just want to show you my thinking compared to the book's thinking. And my thinking is, ultimately, we want to know how things behave. So we want to know the properties. And to better understand the properties, then this, obviously we take observations, we take a theoretical approach to it as well. But ultimately, when we take an observations and theoretical approach, then it boils down to this. It boils down to, we need to know this. If I want to know the properties of an automobile, for example, I need to know what it's made out of. You know, is it made out of aluminum? Is it made out of steel? What is it made out of? Carbon fiber, etc. And so we need to know the composition. But not only do we need to know the composition, but we need to know how the parts are structured. And so basically, when we're thinking about trying to understand matter, you know, well, the first thing is, what is this table made out of? You know, what is this table made out of and how is it structured? Well, this table's made out of atoms. You know, and those atoms are going to have certain properties. You know, some atoms behave this way, some atoms behave a different way. And so we're going to need the properties, composition, and structure of matter. And so, yeah, chemists study matter, its properties, and composition, and structure. Okay, we want to investigate energy gained or released in energy, how energy reacts or interacts with matter. I'd like to know as well. And since chemists deal with matter, well, physics also deals with matter. Biologists, geologists, all the other sciences deal with matter as well. So we often say chemistry is the central science. And here's some things about chemists, employment, etc. Okay, these are the classifications of chemistry. Sorry. But so, for example, one type of chemistry isn't on here. That would be geochemistry. So I started off as a geology major, but I could have stayed as a geology major. I didn't really have to switch my major because what did geologists study? Geologists study matter as well. And so, like for example, these crystals here, we could see now. We look, we take the observations, and then we try to dig deeper. You know, what are the properties of these crystals? Well, they got a color, they got a shape, they got other things. So we try to understand this based on a composition, structure, and a properties approach. And when we think about the composition, structure, and properties, we think in terms of observations, you know, just factual observation. How hard are these crystals? What does it melt out? If I took a torch on these crystals, will they melt? You know? Can I burn these crystals? If I put these crystals into a fire or flame, will they combust? You know? Those would be factual observations. But if I knew this, the more theoretical approach, like say, for example, you know, I know that matter is made up of atoms. I'll just tell you that. And if I know how those atoms are put together, you know, so matter is made up of atoms, and we have different types of atoms that matter is made up of, and I know how those are structured, then I can infer, you know, a lot of things about the properties, so I can take a more theoretical approach to something like these crystals here. And so that would be geochemistry, which would be interested in the matter that minerals and rocks consist of, that kind of thing. It would be geochemistry. We have analytical chemistry, which is like sampling things like water. You know, some matter is pure and some matter is impure. You know, the water out of this tap. Do you see the sign here? What does this sign say? Industrial water, do not drink. Why is that? Because this water is not pure. This water has contaminants. So an analytical chemist, what they'd be interested in is what are the contaminants in this industrial water. Actually, do you know this industrial water is not, this industrial water is just regular tap water. The reason why, do you know why the reason why we have to write industrial here? Is because in order to not write industrial, we have to have a anti-backflow device. We won't talk much about that. Anyway, that's analytical. Biochemists are interested in the matter that makes up living systems. Organic chemists are interested in the matter that's based on carbon. Carbon, the way carbon behaves is it can bond with other atoms in many different ways. And since there's so many different ways that carbon can bond with other atoms, it gets its own unique category. Things like certain chemicals like carbon dioxide. You know, carbon dioxide consists of carbon and oxygen atoms. We'll talk more about that later. But carbon dioxide is considered inorganic versus organic. But methane, you know, methane which burns, which is natural gas, that's considered organic. That consists of carbon and hydrogen. There's inorganic. Inorganic's pretty much the rest of all the elements. There are different types of atoms. These would be the other ones other than carbon. And then physical, chemists are at the bridge of physics and chemistry. So when you learn chemistry, you got to make sure that you have time. The most important thing is make sure you have enough time to study and stay on top of the material. Okay, if this is like, okay, you're committed. Okay, if you're committed to learning about dogs, then you got to start studying about dogs, right? Making the observations, reading close sections. The same thing about chemistry. If you want to learn about how atoms behave, then you better start studying about atoms. You know, this atom's like the Doberman of atoms. You know? Fluorine is like the Doberman of atoms. Versus, you know, hydrogen might be the poodle of atoms, you know, something like that. Although, you know, it could be very deadly, so you gotta watch out. So that's the type of stuff you start studying about that. You know? And so here, when we start thinking about this, we think about things at different levels, you know, because a lot of these things, can you see an atom? You can't actually, the atoms are very small. So when you're breaking the copper piece down smaller and smaller to a single atom, the only way you can see a single atom is using sophisticated instruments. And so here's the sample of boiling water. You got boiling water. if we could see boiling water, water is made up of molecules. These molecules consist of an oxygen atom, which is this red ball, and hydrogen atoms, which are the white balls. And so this would be a molecule of water. Oxygen is not really colored red, and hydrogen is not really colored white. That's just to differentiate it. So those colors are added to that. But when you look at it, it's colorless. There's no color to it. But so this would be an individual molecule, and we have lots of water molecules which make up water here. In order to see the water molecules, we need sophisticated instruments to be able to detect those water molecules and then see the shape of the water molecules. You see the composition, 2 hydrogens, 1 oxygen, H2O. And so that's the structure there. And here, this is the symbolic, this is water boiling. H2O is in the liquid, and then we convert it, this arrow, to H2O, the gas, which is steam over there. So we have different ways of visualizing matter here. Okay, these are the features of the textbook. You can just read through those features, and we'll look at some of the features as we go along. But let me jump to chapter 2 really quick here, and just chapter 2 deals with matter and energy. You know, chemists study matter, yes, but they also study energy. Is energy matter or not matter? Well, when we think about this, I got to think of a form of energy. One form of energy is the light coming from the light bulb. Is the light coming from the light bulb, and I see the light coming from the light bulb, or this projector here, is that matter or not matter? The light is not what we call matter. The light we would call energy. It's just the energy being transmitted in the form of light. But even though I said chemists study matter, matter interacts with light. And so since matter and light interact, then chemists are also interested in studying energy as well. Not only that, we get energy when we combust things. When we burn things, energy is released. Sometimes we consume energy, like when we melt ice. When you melt ice, you got to consume it. When you boil water, you consume energy. And so the interaction of energy and matter is very important. So we're going to look at that. All right, this is a typical chapter. A typical chapter begins with learning objectives. Chapter 1 didn't, because chapter 1 is kind of short. What was the learning objective? This is what I do after class. After class, I'd go, okay, what was the take-home message of chapter 1? What was the take-home message of chapter 1? The scientific method. Okay, what is the scientific method? What are the steps in the scientific method? Observation, pattern, law, hypothesis, theory. Okay, what is a theory? Well, we define that. Give me an example of the scientific method. Give me an example of the scientific method. It doesn't have to be a new one. Just what was the example I gave? Well, I guess the Doberman. Oh, Doberman isn't good because, you know, like oxygens behave like oxygens, you know, but Dobermans, they'll have a unique personality to them. So Dobermans are a lot more complicated system than an oxygen atom. When you look at an oxygen atom or an oxygen molecule, all oxygen molecules behave like all other oxygen molecules. So it's a lot simpler than a Doberman. But an apple falling from a tree, do apples have an individual personality? Well, apples are going to have different weights, but you know, when you look at an apple, the same size apple falling from a tree, is that all over the place? Like, is that a friendly Doberman or not a friendly Doberman? That kind of thing. And so, so what was the example that I used? Yeah, the apple dropping from the tree, which led to what? Which led to patterns, which led to Newton's law, which led to gravity. So you give an example. So that was the take-home message. The other take-home message is that, you know, the organization of chapter 1 is a little different than the way I'd like it organized. Okay? Well, these are the kind of the take-home points that you want to get from chapter 2. Identify and explain the differences between interpreting and describing matter at the macroscopic, microscopic, and particulate levels. So these words, macroscopic, microscopic, and particulate. Define the term model as it's used in chemistry to represent pieces of matter too small to see. Identify and explain the differences among gases, liquids, and solids in terms of macroscopic level properties, shape and volume, particle movement, and particle spacing. here. Distinguish between physical and chemical properties. Here we go again. Physical and chemical properties, the two types of properties that we look at, physical and chemical. Physical would be like, what's an example of a physical property? Boiling. Yeah. Chemical property, what's an example of chemical property? This is where they talked about the change of one substance to another. So if you take methane and burn it, do you still have methane? No. If you take water and boil it, do you still have water? Yeah, just in the form of steam instead. So that's the difference. At both the particulate level and the macroscopic, distinguish between physical and chemical changes at both the particulate level and the macroscopic level. Distinguish between a pure substance and a mixture of both the particulate level and the macroscopic level. Distinguish between homogeneous and heterogeneous matter. Describe how distillation and filtration rely on physical changes and properties to separate components of mixture. So what you're looking, by scanning this, you scan this and you're looking for keywords, keywords that you want to remember. Distinguish between elements and compounds. Distinguish between elemental symbols and the formulas of chemical compounds. Distinguish between atoms and molecules. Here, not everything consists of molecules. We got atoms. Not only that, we have compounds. Not all compounds are molecules. State the law of definite. Okay, this is a definite or constant composition, and explain its implication with how compounds and mixtures differ in composition. So this is the law that came from the theory. Match electrostatic forces of attraction and repulsion with combinations of positive and negative charges. And so all we're doing is we're just trying to register keywords that we want to remember when we study this or try to learn this. Distinguish between reactants and products in a chemical equation. Distinguish between exothermic and endothermic changes. Distinguish between kinetic energy and potential energy. State the meaning of or draw conclusions based on the law of conservation of mass. State the meaning of or draw conclusions based on the law of conservation of energy. Chapter 2 is long, and so that's where we got. And so let me just finish with this slide. Matter. Matter is the material that makes up the universe, and everything that has mass and occupies space. So let me just ask you this: is the air in this room matter? Well, it occupies space, but does it have mass? Is air weightless or does it have mass? It seems like it's weightless, but it does have mass. I mean, if you stuck your hand out the window when you're driving, do you feel the air? Yeah, you got to push all the air molecules out, or the air atoms, or whatever the air particles consist of. You got to push them out of the way. And so, yeah, air. Whereas if we had a vacuum, is vacuum matter? You know what vacuum is? Vacuum is totally empty. If you sucked all the air out of this room, you'd be left with a vacuum, and there's nothing there. So vacuum. But anyway, when we look at matter, we can look at it at the macroscopic, microscopic, or the particulate level. And so this is what we'll start off next time talking about it. But I'll end here.